In the previous lecture, we have discussed the nomenclature of the basis set. Now, the question is where to get this basis set. Your go to site will be the basis set exchange.org. So, if you go to this site, this is how the site looks like. Now, here you see it has basis set for almost all the periodic elements. Now, the same basis set may not be available for all the elements. So, you have to make your selection like that. For example, let us say if I think of 631G, this basis set may not be available for heavier elements. So, if I select uranium, you will see that there is no 631G basis set available. So, this is a problem. Sometimes you cannot get the same basis set for everything. Most of the cases, the def2 basis sets are available for most of the elements. Let us say for selenium, you will get the so called TZBB basis set and def2 SBP basis set also. For the selenium also the def2 SBP is not available, but I think you will get it for argon. You see these are the def basis sets available, and what is JK fit or what is RI fit will come into that. The correlation consistent basis sets are available for few of the elements. Let us say for zinc, I know the correlation consistent basis sets are available. You see for this is augmented, correlation consistent, even the 6311G basis sets are available. Now, before going any further, first see what are how these basis sets are there. So, different software uses different format of the basis set. Advantage of this site is that it gives you basis set for almost all the possible popular quantum chemistry software. It even includes the Orca. So, let us say if I want to get for hydrogen the CCPV-DZ basis set, this is how you should go, and this is how the basis set looks like. It is hydrogen. So, it has it contains the first shell of S, the STO contains 4 Gaussian, the second for S, the second one contains 1 Gaussian and it has 1 P function. Now, let us go back to this table. You see that for CCPV-DZ it is 2s, there are 4 S primitives and 2s 1P contracted. So, that means if I go back to here, you can see that there are 4 primitives which has been contracted into one Slater type of orbital, and then there is another Slater type orbital. So, there is 2 contracted Slater type of 2 contracted Gaussian type of function and 1 contracted Gaussian type of P function. Similarly, if I go to triple zeta for hydrogen, CPV double zeta, T must be below, here it is. If I get the basis set, may not be very clear from the picture here. It says 3s, it is 5s contracted into 3s 2p 1d. These are 5s, this has been contracted into 1s type of function, there is another 1s type of function, and there is first s type of function, to total 3s type of contracted Gaussian, 2 contracted p type of Gaussian and 1 contracted d type of Gaussian. So, that is how this orbitals, these basis sets actually looks like. So, you can download this basis set and put it in your input file and perform calculation with that. Before actually running the calculation, let us see what are the basis set which are inbuilt in Orca without putting this external basis set, what are the basis set you can use for your calculation. So, in Orca the basis set input is given like this. So, the basis set block start with a percentage basis and the name of the basis set has to be given within this double quote. What this auxiliary basis set is we will come to know in the next week's lecture, and the block must be ended with an end statement. So, most of the time there can be an error if you do not close this basis set block or any block for the in Orca without an end statement. So, what are the basis sets available in Orca? To see that, you can actually go to this site, the Orca manual. So, if you see this table, you will see for which elements the basis sets are inbuilt. So, to use this basis set for this particular elements, you do not need to put any external basis set. You can directly use the basis set name and this will give you the proper external basis set out of it. Next is that how to change a basis set, give a particular basis set for an atom. So, the first way you can give it by putting the basis set name here in the top line, but if you want to change the basis set of a particular element, you can use this statement in the basis set block where new GTOC. This would overrule the previous assignment what is given from the top line, and for this particular element it will change the basis set to def to TZVP. If I do not want to change for all the elements of a particular type, let us say I have this H2 molecule and I want to change the basis set for one of the hydrogen atom. So, in that case I do not need to use the basis set block. In the XYZ file only I can use this statement new GTO and Zora def to TZVP, and by using this I can specify the basis set for a particular atom. The basis set for other atoms of the same element will remain unchanged. So, I can directly put new GTO and, or if I want to put a basis set from basis set exchange library, I can either give it in the basis set block as new GTO, or I can give after the XYZ file also. Do not forget that if you are using the basis set like this from the basis set exchange, and in the basis set block you have to end it with do end statement. One end statement will only end the basis set, not the basis set block. So, this can lead to also an error. And if you want to add extra functions, let us say if I want to add an extra D functions, I can add for all the carbons by using like add GTO statement. So, what this add GTO statement will do, how this is different from the new GTO is that if you use new GTO statement, it will replace the entire basis set, whereas the add GTO statement will take the already existing basis set and add these additional functions on the top of it. And similarly, if I just want to change it for a particular atom, not for all the elements of same type, I can add it in the XYZ file like add GTO basis set. So, we have discussed the case of methane and we have told that we have calculated how the basis functions actually look like. So, let us now make the input file, run the calculation and let us see if it matches with the whatever we have discussed. So, let us go to Avogadro, drawing methane is generally the most straightforward. If you give it, it will only give you methane. I go to Orca, I change the basis set to 631G. I make a new folder called basis set. And I keep it CH4 631G. So, I go to the basis set folder, I open in terminal, and I run the calculation. CH4 631G dot INP CH4 631G dot out. My calculation is done. So, let me open the output file. So, this is 10s 4p contracted to 3s 2p pattern. So, there was total 10s function and that is contracted to 3s 2p, and there are 4s which is contracted to 2s pattern. So, it is basically 10 and 4 3s are 12. So, it is 22 and 4 into 4 for 4 hydrogen is will be 16. So, total will be 38 Gaussian function. That is what we got from our calculation. Now, check the number of Slater. So, my number of Slater is same as the dimension of my basis set, and that is called, now in this case we have calculated it to be 17. So, you have got the number of basis function and the number of Gaussian, what was our expectation. Now, just check the energy is 40.180. Because of the variational principle, the larger the basis function is, the energy will go down. So, let us do the same calculation, this time with 6311G basis function. So, now rerun the calculation again, this time with one extra G, one extra value of 1. So, if I now open it, the output file, first check the number of Slater is 25. That is what we got from our calculation. Remember CH4. So, now see the number of Gaussians. So, it is 11, 5 3s are 15. So, it is 20, it is 26, and then there are 5 S functions which I multiply will be 20. So, the total number of functions will be 5 3 are 15 plus 11, it is 26, and its 5 S is there. So, total number of things will be 46 in the present case, and this is my number of Slater function in the present case. Let us check the energy now. So, my total energy in this case is 40.18789, and the previous case is minus 40.180. So, because I have increased my size of my basis set, it has lowered down my energy a little bit. So, this is what happens when you increase a larger basis set, it will give you lower energy. So, in this class we have learned about basis set, we have learned how to select a good basis set for your calculation, and you can use what we have learned from this class to decide the basis set on all the calculations we will learn about this thing. But we mostly discuss in these cases for energy and geometry and polarizabilities and dipole moment. There are special properties where you may need a special kind of basis set, especially when we will be considering relativistic effect. So, we will learn about them in the coming class. The other topic which we completely skipped in this class is the basis set superposition error and complete basis set limit, how to extrapolate them to complete basis set limit. They are more relevant when you are using a wave function based method, wave function based electron correlation methods, because your methods are, your results are more sensitive to the choice of your basis set. So, after we know what is electron correlation method, we will come back to this topic of basis set superposition error and extrapolation to complete basis set limit. See you in the next week.